Here's what's actually on the line in 2026. Your AI agent finishes a session. The next day, you ask it to recall one specific detail, and it fails. Not because the memory is gone, but because the system buckled under the weight of its own processing. This exposes a critical failure point in modern agent architecture. The system successfully locates the exact memory you asked for, but it cannot apply that information to the task at hand. Look at these two gauges from a recent benchmark. A memory system retrieved the correct source material 85% of the time, yet it answered the user's prompt correctly only 32% of the time. It found the data, but it failed to remember the specifics. The root cause isn't amnesia. The agent still has the file. The problem is that it summarized that memory into a form that stripped out the specific facts required for complex reasoning. This gap between finding a memory and utilizing its details is a primary failure mode in modern agent design. I'm the bearded AI guy. This series breaks down the human architect's work in AI agents in action, and today we're on day 2 of the memory stack, episodic memory. Episodic memory is the agent's explicit, time-indexed record of specific past events. It tracks exactly what happened, when it happened, and the conditions of those actions. Think of it as a raw journal, not a textbook. A textbook contains stable facts. The journal is the unedited story of a session before any abstraction takes place. When you expect agents to remember user interactions across days and weeks, designing that unedited journal to scale is mathematically much harder than maintaining a database of static facts. To understand why it's so hard, we have to start with the constraint that shapes everything. The model is frozen. Its core weights never update between sessions or user requests. Because the model cannot learn internally, any memory of your Tuesday request must live entirely in an external database. It is then selectively reintroduced into the prompt at runtime. The common developer instinct here is to brute force the problem. Just use a massive context window and keep all the session data loaded. The lost in the middle evaluation data shows why this fails. Even in state-of-the-art long context models, accuracy drops severely when a vital fact is buried deep inside a large block of text. Episodic memory prioritizes precise attention placement over sheer storage volume. You keep the vast majority of data outside the model and retrieve only what is necessary to execute. Start with the cleanest blueprint we have. An effective episodic memory functions like a time-stamped journal. When the agent needs to recall something, it doesn't read the whole book. It flips to the specific pages that matter right now. This is the Generative Agents architecture from Park and colleagues. In their system, every single observation is appended as natural language to a continuous stream. Vector search alone cannot surface the right context. Instead, each memory is ranked by 3 separate signals at once: semantic relevance, recency, and importance. It doesn't just store raw data. Periodically, the agent triggers a reflection cycle where it synthesizes those raw observations into higher-level insights and injects those back into the stream. This continuous loop of capture, retrieve, and compress forms the baseline spine for any functional external memory architecture. But compression has a steep, hidden cost. Compare 2 ways to store a chat session: saving the raw, unedited footage versus saving a polished incident report. The incident report is shorter and cleaner, but the summarizing agent permanently deletes any detail it deems non-salient at the exact moment of writing. The LoCoMo benchmark puts hard numbers on this flaw. When retrieving session summaries, the system hit a high recall score of 84.7, but a low answer F1 score of just 32. Retrieving raw observations resulted in a lower recall, but a much higher F1 of 43. The text remained fluent, barely dropping on the Rouge L metric, but the summarization caused a massive 10-point drop in fact score. The summary had already thrown away the exact factual details required to answer the prompt. Retrieving highly compressed summaries creates an illusion of competence. The agent reads fluent text that is silently missing the hard facts it needs to execute. You can learn from failure without bloating the context window or destroying the facts through bounded reflection. Think of a coach writing down a few post-game notes to read right before the next match, instead of rewriting the entire playbook. The reflection framework executes this in AlfWorld by relying on a highly constrained mechanism to handle failed tasks. When a trial fails, the system reads the failure logs, generates a concise verbal lesson about what went wrong, and appends it to a memory list. On the very next try, the agent prepends the prior lessons directly into the new prompt with a specific memory tag. The architectural secret is rigorous bounding. The updater strictly truncates that context to only the last 3 reflections. Effective runtime learning for a frozen model relies on replaying explicitly bounded lessons to step the trap of infinite context bloat. An append-only memory system is like a closet you never clean. Eventually, the sheer volume of noise makes it impossible to find anything. The operational costs are staggering. Running just a few simulated agents over a couple of days generates massive token costs and unbearable latency. Selective extraction, used in systems like Mem0, implements a governance gate at the write path, storing only data that raises expected future utility. By filtering noise before it is saved, this approach claims a 90% reduction in token cost and a 91% reduction in P95 latency. These leaderboards should be treated with caution. Competing vendors like Zep point out that simple add-only systems often fail to resolve semantic contradictions when facts change. While vendor benchmarks are directional, the fundamental engineering mandate remains. Ruthless governance and aggressive deletion at the write path are required to prevent memory degradation. Pull these concepts together and you get the blueprint. Episodic memory for a frozen agent is an external store ruled by a strict policy. Write, retrieve, compress, and forget. The stream provides temporal structure. The F1 drop warns against overcompression. Reflection proves bounded loops work, and the governance gate enforces deletion. This moves the priority from storage to selection. The designer must determine which event representation is worth the compute cost to revisit. When you precisely govern exactly what hits the context window and in what form, memory transitions from a liability into your agent's greatest advantage. If you want to see how we translate this chaotic episodic journal into stable, long-term knowledge, subscribe to the channel for Day 3, where we cover semantic memory. I want to hear from you in the comments. In your own agent architectures, are you storing raw footage or polished incident reports? And what broke when you chose the wrong method? This entire framework comes from the Human Architect's deep dive in the book AI Agents in Action. The next time your agent forgets a crucial detail, don't ask whether the memory was saved. Ask whether you kept the footage or only the report. That choice at the right path sets the ceiling for an agent's reasoning capabilities.